All right, so it's recording. And so let's talk about, I know a lot of you from Chem 1A, but if you haven't had me before, but let me just give you a little bit about my background. And so I started college at SBCC. Anybody know this? Yeah, Santa Barbara City College. I started off as a geology major. And when I was taking mineralogy, that's when I decided to switch to chemistry, because in mineralogy you have to identify these minerals based on the shape of the crystal. And that was okay. You have little magnifying glasses. You can look at the crystals. The color of the crystals. The color is deceptive, so what you do is you scratch it into a fine powder. And the fine powder is consistent as far as color goes. Otherwise, the color changes depending on how big the crystals are. And so you do the scratch test, and then you test some chemical properties. Actually, you have a bottle of HCl. Does it react with HCl? And so you try to identify these minerals based on looking at those properties. And that was pretty tough. And I remember the mineralogy professor, he said, there are people with 30 years of experience who still misidentify minerals. And I thought, boy, that just seems so ancient. I mean, I was taking chemistry at the same time, and in chemistry, they're talking about more sophisticated instruments, things that allow, like X-ray diffractometers, allow you to identify minerals quite rapidly. And I thought, why? The geologists don't have access to these tools, or the chemists do? So then I switched, but that was very naive because, later on I realized that the geologists use the exact same tools. I mean, in fact, a lot of geologists that I worked with were doing things which are chemistry. So they could have called themselves chemists. In fact, they did. A lot of them were geochemists, so they were doing chemical problems in geology. But after a while, I mean, when you get to graduate school, you realize that there's not really any boundaries. It just kind of blends from one field to the next. And so you have all different kinds of people working in geology, engineers, structural engineers, whatever, and all kinds of people working in chemistry. On the same floor, there was an electrical engineer who was doing biochemistry, and this is stuff that interested him. And so I started off there, then I transferred to UCLA, where I got my BS in chemistry. And then I went back to Santa Barbara, actually, because there was an interesting project there. And I got my PhD. I got my PhD in inorganic chemistry, so maybe this is a good time. Inorganic/analytical. Actually, the group I was working in was called a physical chemistry group. And so physical chemistry is like the boundary between physics and chemistry. And my advisor at UCSB was a physical chemist. He did lots of physics type stuff. But I did a lot of inorganic synthesis. Now, inorganic, what's the difference between inorganic chemistry and organic chemistry? Yeah, organic chemistry is carbon-based. I mean, carbon, because of the way it bonds with 4 bonds and it can link to itself, the types of structures you can get are quite numerous compared to a lot of inorganics. Inorganics often have limited bonding. For example, oxygen hates to bond to itself with single bonds and form long links of oxygen atoms. And so, because of the richness of carbon chemistry, they subdivided that into a separate category. And so when you look at the number of organic chemicals that are found in nature and the number of organic chemicals that are being synthesized, new ones being synthesized every year, it's huge compared to the number of inorganic chemicals that we have. In general chem, we spend most of our time discussing inorganics. But a lot of the chemicals that you deal with organics, so we throw in a few organics in there. All right. Well, let's talk about the course next. Let's take a look at the syllabus. The book is if you have the full text, you don't have to buy a new book. If you have the half text, then it's the second half. The second half, well, in Chem 1A, we left off with Chapter 13. And so we should start Chem 1B with chapter 14, but we aren't. Actually, if you look at the syllabus, we're going to jump all the way to chapter 24. We're just going to cover the first 3 sections of chapter 24, which isn't that much stuff. It's just the basic structure and nomenclature of coordination and complex ions, coordination compounds and complex ions. Okay, those are quite common, and we want to know how to name these before we start talking about them in earlier chapters. So that's why we're jumping to 24. And then we should swing back to 14, but we're going to skip 14, and we're going to start 15, and then go 15, 16, 17, 18. Those 4 chapters, right? The reason I did that is this is kind of funny because we were at a meeting last week, and they were talking about the math prerequisite for anatomy and physiology, and so the math professor, not the math professor, but the anatomy professor said, "Oh yeah, there should be a math prerequisite because you have 2 kidneys and 2 lungs," and it's just so funny because what would you think the math prerequisite for anatomy is? They're talking intermediate algebra, but I don't know. Do you really need intermediate algebra for that? Well, you'll need it for this class, though. So, what was I talking about? Yeah, 15, 16, that's 4 chapters. These 4 chapters I like to cover right at the beginning because they deal with the same type of calculation. And so in chapter 15, we do what's called a basic equilibrium calculation, and then it gets more and more advanced. So by the time we hit chapter 18, we're doing quite complicated equilibrium calculations. And so this is a little warning or forewarning, is that make sure you have the basics down. And so you don't want to fall behind in this series, because if you don't get chapter 15, then you're going to struggle with the remaining chapters. It's going to be very difficult. So in Chem 1A, you might have struggled with one chapter and just blown it off and still pass the course, but you can't do that with this series. You can't blow off chapter 15 because there will be 4 chapters worth. Okay, then we're going to go back and cover chapter 14, chemical kinetics, which deals with the speed of reactions. And then go back up to chapter 19, which is thermodynamics part 2. Chapter 20, electrochemistry, and then back to chapter 24. We're going to finish that. And finally, we're going to end with chapter 25, nuclear chem. And so chapters 21 through 23, we're just going to hit a page or 2 at a time. It's more descriptive chemistry. And so I'll be inserting those topics throughout the semester. But we aren't going to cover those chapters in full. Nor are we covering 26, 27, I think, which is like biochemistry and organic reactions.
Can I make a quick announcement?
Yeah, go ahead.
Hey, do you guys have your own textbook? Because I have that big general chemistry textbook that's good for his class. $40.
I think you should go to the Chem 1A class, I think. Or actually, did everybody get this? If you got the big one, then it'd be more profitable for them in 1A.
Big posters, you can sell it for a lot more too.
Yeah, but it doesn't have mastery in chem.
Okay. All right, thank you. But let me know. I can send him an email if you're interested in that. So one of the things you're probably thinking, what are the exam dates? When's your first exam? And I don't have any of the exams written here, the exam dates, because it's going to be very easy. Yeah, every week. You're going to have an exam every Tuesday.
We're going to have an exam every Tuesday?
Yeah, starting next week. So your first exam will be a week from tomorrow. It's not like a 6-page exam. It's only going to be like a 2-page exam. And the exam, flip to this course information sheet, page 2. All right, I figure we're going to have 14 exams, each worth 40 points. And so that's going to give us a total of 560 points. If you thought that's a lot of exams, well, maybe you should call it, maybe they're quizzes, more like 2 pages.
They're just called tests.
Tests. Okay, tests. How about tests?
Less stressful.
Yeah, you're right. Tests sound less stressful. I like that.
That's not even as bad.
All right, a test every Tuesday. How about that? And then we're going to have a quiz. This is going to be easy too. A quiz. We're going to have, if I can keep to the schedule, I'd like to have a quiz every day.
Oh my God.
Maybe I should call it something else. I'll make it less stressful. Let's call it a question. A question every day. Questions every day. Starting tomorrow. And so you're going to have 40 of these if I can stick to it. And so tomorrow, what can you expect? Just you can expect one question worth 2.5 points.
Like where's the action?
Okay.
Is it whatever we covered?
It's whatever we covered the day before. And so whatever we covered today, you're going to be quizzed on it tomorrow. But I'll make it even less stressful because these are open notes. Closed textbook. You can write whatever you want in your notebook. Don't photocopy the book. Microfiche or something. These tests, though, these are going to be closed.
No, it should be the opposite.
Closed notes. Just something, from the previous day's notes. You can write book notes in there, whatever you like. So those shouldn't be too hard. Those should be easy points, I hope. All right, then we have our final. The final exam is going to be closed notes, closed book, and it's going to be comprehensive. So we'll cover everything from the beginning to the end of the class.
Do we get to keep the test after the exam?
Yeah, the test, not the final though. I hold on to the final.
Just to study for the final.
Yeah, yeah. You can keep the tests. In fact, what I do is I post old tests on Piazza. Are you guys familiar with that?
The baseball player?
No. There's a website called Piazza.com. I used to use the team sites. Are you familiar with that? My ECC team sites. I don't use that anymore. I've just been using this Piazza, and so I'll post like PDFs of old tests. I'll post keys here, announcements, whatever else. And so when you go to Piazza.com, you look in the search windows, and you'll pull up El Camino College, and then it lists all the courses at El Camino that have a Piazza site associated with them. And if you log on without the invitation, then you'll look for my class, and then the access code, I think I called it Chem, what did I call it? I call it ECC Chabal Chem 1B, something like that. But you don't need to know what it's named because there aren't going to be too many chem classes. I think there's probably only going to be one on my class. And so the access code is Chem 1B, all lowercase, no spaces. So, also, if you have questions, you can post this here. I'll check it. It sends me an email. update every couple of hours. All right. So is that clear so far? All right, go back to this course information sheet and let's take a look at some of the other required assignments here. So we talked about the exams and the quizzes. Okay, next is the homework. In the past, what I've been doing with the homework is I've just been collecting. And I collect the Mastering Chem homework, and then I supplement the Mastering Chem because the Mastering Chem doesn't have all the end of chapters, so I threw in some end of chapter problems. But this semester I decided to do it a little differently. I got some complaints that the homework assignments were a bit tedious for some people, and for others it was quite good. And so it depends on what your level of preparation is, how comfortable you are with material. And so this is Chem 1B, and what I'll do is I'll just leave it up to you, how much homework you want to do. Let's say, for example, in section 20.3, it was pretty tough conceptually. Well, if 20.3 was tough, then you want to do every single homework problem in section 20.3. And not only that, you might look for other books and see how they present that particular section. That's one way of doing it. The other way of doing it, and this is what I did as a student, I did all the homework problems, so every single one. That's over 100 problems in our book, and so how could I do it? How could I? Well, I had to change, and this is what I did because I was taking a lot of classes, and I was talking to other students in the class, and some of them were doing, getting the top score. I wasn't after I transferred to UCLA. I was struggling, in particular in thermodynamics. And so I asked them, how they study, how they prepared, what their background was, is this review or is this all new stuff? Because, I spent every single hour, waking hour studying, and yet, my grades weren't showing it. I was thinking, what am I doing? Am I dumb? Am I not working right? Initially I thought it was dumb until I started talking with them, and then I realized, no, I could learn this stuff as well. I didn't have the same background they had, so I had to go back and review a lot of the basic stuff in the Chem 1A book at UCLA, which was a lot harder than the Chem 1A book that I used. And so I got that background information. And then I finally felt, okay, now we're starting to level the playing field. So I didn't feel like, oh, this guy's a genius and I'm an idiot or something like that. I felt, okay, now I feel like I can get top scores as well. And then something else that caught me, I noticed a lot of them did every single homework. And for me, that was absolutely impossible because one homework problem could take me an hour, and I might not even get it. I'd have to sit on it and think. And so, how could you do it? 100 problems, potentially an hour. That's 100 hours. Impossible. But one thing that was quite different at UCLA was, almost every class I had there, if there was a solutions guide, they gave the complete solutions guide, not the partial solutions guide. When I was at SBCC, I was taught, don't open the solutions guide. Give it an hour, give it more time, and then think about it. And your brain will work at making those connections. And, that's good advice. Your brain will work at making those connections, but unfortunately, sometimes your brain makes those connections after the final exam, which happened for me quite a lot because, I know I told this story in Chem 1A, but, after the final, I went over to Ralph's to buy some stuff, and when I was in the checkout line, boom, it hit me. That's how I could have solved that problem on the final. I'd just taken the day before, but it's too late. And so then I was thinking, if it takes that kind of time, then how can I speed things up? Well, talking to these other people, I realized this is how you speed it up. You look at all the problems, and you don't look at them right before, the night before the exam. You look at them early on, and then your brain has the time to make those kind of connections. And so after I started doing that, then things became a lot easier. But it was a struggle because at Santa Barbara City, I worked hard here too. And so I tried to get on the dean's list every semester, and it was okay. But when I got to UCLA, I worked extra hard because everybody said your GPA is going to drop 1 unit when I went there. And so I worked extra hard and was still struggling. So, but to make a long story short, then once I changed all those study habits, then I was consistently on the dean's list at UCLA. So that was good. Okay, so I'll leave it up to you. You might try it and see if it works. You have the full solutions guide. You can look at every single problem and go from there. But what I'd like to do for your homework is whether you do a little or a lot, you're still only going to get 4 points per chapter. And it's 10 chapters. If you turn in nothing, you'll get nothing, 0 points. So turn in something so I see that you're trying.
What about Mastering Chem?
Mastering Chem, the same thing.
This homework and Mastering Chem?
No, whatever works for you, because on Mastering Chem, I put just tutorial problems. So let's say this stuff is easy, you don't really need to do anything, just skip it. And then this stuff is a little more challenging. Mastering Chem counts. It counts. It's just the way I count it.
I think he's wondering if you're allowing us to do whatever we feel on this review.
Yeah. What you have to do is you have to do like an analysis. Where do you stand? Your own self-assessment. I need more work on these type of problems, and so you should do that on Mastering Chem. For example, in Mastering Chem, there's different tutorials. So there's a nomenclature tutorial or writing formulas tutorial. But if this nomenclature and writing formulas is easy, then skip those and look at the structural. Or in other words, you could do either. You could do no Mastering Chem and out of the book, or you could do nothing out of the book and Mastering Chem, or you could do both, Mastering Chem and out of the book. What I would do is I'd do both, Mastering Chem and out of the book, because I really doubt everybody's going to be a master at all the types of calculations that we have. You'll still get the same points, right?
That's my question.
Okay. Unless you don't turn anything in. Yeah. This is something new because I got so many complaints about homework. The homework's so tedious, it's such a waste of time. And so I'll leave it up to you to do. But, I'm going to check it and see. And if I see, okay, on the exams, it's clear that you aren't getting certain concepts and you aren't doing the homework, then I'm going to connect the two dots, basically. Okay. All right, the lab, let's take a look at that. The labs are going to be 15 points per experiment. And so you'll come in, do the lab, and then turn in a report. Most of the reports are going to be fill-in-the-blank type reports. Just complete the report sheet in the lab manual itself. Except for 2. There's going to be a qualitative analysis lab. The report for that's very simple. Well, for me, I think it's very simple. For others, it's kind of long. But you have to write, qualitative analysis is a series of chemical reactions that allow you to identify certain unknowns. And so you'll write all the chemical reactions out, and then you'll tell me what cations you found in your unknown. And so most of your grade is going to be based on, did you identify the correct ions? And then a little bit will be, did you write all the correct chemical reactions that occurred in identifying those? And so that's going to be worth 50 points. And the other report that you're going to write, this one's going to be a bit long, is the titration report. This is going to be a formal scientific report. We'll talk more about this as we get closer to it. Okay. The grades, a 90 is the cutoff for an A, guaranteed A, 80 for B, 65 for a C. The C cutoff really isn't adjusted, but the 80 and 90 depends on the point distribution, so those might be curved a little bit. Okay. All right, and then you can read through the rest of this sheet here on the back, but let's flip to the front here. For the required materials, we need the book. Here, either the full or the half text, part 2. We have the Catalyst, which is a lab manual. This one's a little bit more expensive than the Chem 1A manual. It's custom published, so I think it's about $27. You'll need a composition book like this. I prefer these quad-ruled composition books with sewn binding. If you have the one from Chem 1A and you still have some empty pages, go ahead and use that. This is a Chem 1A book here. Let's save the first page for a table of contents. If you need more room for Chem 1B, you can insert another page if you want. Just save the first 2 pages. Okay, and then have some room here for your notes. I like quad rule because it just makes tables easier to draw. And sometimes we make little graphs in here, just qualitative. So let's see if I can find a graph. Here, some graphs. You might get a second one for your homework if you want to keep it all in one place. Safety goggles. The ones you have from Chem 1A should be fine. Scientific calculator. All right, for Chem 1A and 1B, we require a non-programmable calculator. I recommend this one, or the equivalent. And so the calculator I got this at, I think, Rite Aid. And it's the Casio FX 115 ES Plus. This wasn't the cheapest. This was, I think, was about $18. And so the difference between this $18 one and the $15 one is this $18 one has an equation solver. The equation solver that you want is for quadratics. And so if you get this one, it's going to make your life much easier because all you have to do is plug in A, B, and C, and it gives you x1 and x2. Unless you like solving quadratic equations by hand. If you do, then any calculator is fine. But get this, or TI has one, and Sharp. All the calculator manufacturers have one. So just look for it. Okay, item 7, a Sharpie pen is handy to have for labeling glassware. We're going to do, in qualitative analysis, we're going to be using all the test tubes on your test tube rack. So you just got to keep track. You don't want to get them mixed up because then you'll get some errors and some weird results. Recommended materials, 1 lab coat or apron. At some schools, I think like Santa Monica College, for sure UCLA, and a bunch of other schools are still, are starting to require lab coats. And this is a result of the accident that happened at UCLA. Did you hear about that? No? Yeah, there's a student who just finished her bachelor's degree in chemistry, and she was working as a research assistant in a laboratory at UCLA before applying to medical school. And she was working with pyrophoric materials. Do you know what pyrophoric materials are? The pyrophoric materials...
Is this the girl with the sweater?
Yeah, right.
Okay.
Pyrophoric materials ignite into flames upon immediately ignite into flames upon contact with air. And so all you have to do is expose them to air, and you'll get a fire. That being the case, you have to work with pyrophoric materials in an air-free environment. In an air-free environment, there's like a rubber septum that they put over these. And so what you do is you put a rubber septum, and then you poke a needle in here, and you flush, and then you have an exit needle. You flush this container with nitrogen or argon or some other inert gas. Okay, then you get another syringe, and then you inject your pyrophoric material. So now this is air-free, right? If it's full of air, then you'll have a big fire. Well, apparently she had a big syringe. I think it was like a 25 milliliter, or maybe more. It's a fairly large syringe, and she was drawing it out to max capacity. You know, when you draw out these pyrophoric materials, you're only supposed to use about a third or a half of the syringe. She was using the whole thing. And so, from what I heard, is maybe either the plunger popped off or it started squirting out because it was too much in there. And as it started squirting out, it's like a flamethrower. It just ignites into big fire, string of fire. Well, she was wearing a sweater or clothing that was flammable, like rayon or polyester. I'm not sure what she was wearing, but all her clothes caught on fire. And then she, I think she survived for about 1 or 2 weeks after that before succumbing to that. And so lab coats are good because lab coats are obviously flame resistant. Cotton's good, you know. So in lab, if you don't have a lab coat, then wear cotton clothing because it's harder. Avoid the synthetic materials. Not that we're going to be working with pyrophorics, but we'll be working with some flammable materials like ethanol and some other stuff. Okay, Bunsen burners. All right, so you might consider that, especially going into organic, if you're continuing that way. It's good to get. All right, item 2, nitrile latex disposable gloves. I'll have a few boxes of those available. You can just reimburse me for cost, or you can bring your own, either way, if you want to use them. If not, that's fine. All right, any questions on the syllabus or the course information?
For your office hours?
Oh,
Have
yeah.
a time what does it?
Yeah. Can you pen that in?
Yeah.
The office hour, actually on the syllabus I do have some times.
Thank you.
All right, that's Tuesdays and Thursdays. I also have office hours Monday and Wednesdays after class, so I'll just stick around for as long as people want, Monday and Wednesdays. Except for today, I have to leave right at 2:30. And so my office hours are just following class every day, both the morning section and the afternoon section. You'll have to look for me, though. The office hours are, Chem 120 is my office, which is just across the hallway here. Chem 105 is this room. Do you know which room Chem 108 is? My office is a mess, so sometimes I have my office hours in Chem 108, which is the computer lab. And Chem 162 is our lab. So just look for me around there. You can also schedule an appointment if you want to do it that way as well. All right, let me show you a couple of things if you're not familiar with Mastering Chem or Piazza. All right, this is Piazza here. This is free. And if you go to Students Get Started, it'll walk you through how to register for the class. And so you just search schools. So I'll type in El Camino. And then you can see it, El Camino Community College District. There are only 5 classes on campus that are using Piazza. And so, did I do it right? Well, just click around here and you'll be able to add, and then punch in this access code here. If you have problems, we'll go through it later. Okay, that's Piazza, and then we have Mastering Chem. All right, I have the assignments up here. Chapter 24, Part A, 15 through 18. Oh, this didn't go in order. From 18, we drop down to 14 here, and then 19, 20, 24, 25. The due dates, I had them all due on the same day, but on the day of the test, I'm going to just check, how much homework did you do? Okay. But the due date, the official due date is going to be at the end of the semester. What does it say not available? It's the wrong class, sorry. Oh, you'll find it. All right, the other things Mastering Chem has, in addition to the homework, are these. Class resources. And so we'll go to chapter 24 here. And then if you look at chapter 24, my version has the e-text on here. You may or may not have that thing. But there's a practice quiz 1, practice quiz 2, glossary flashcards. You can self-test yourself. Focus on sections, selected solutions, answers appendix, lecture PowerPoint. Let's take a look at the lecture PowerPoints. And so you can download the lecture PowerPoint for chapter 24. For chapter 24, I'm going to use some PowerPoint slides. For chapters 15 through 18, I'm not going to use much PowerPoint. It's mostly going to be on the board. But there's some structures here, so this is why I'm going to show this. Well, chapter 24 deals with complex ions and coordination compounds. So the first thing is, what are complex ions? What are coordination compounds? Complex ions and coordination compounds give this mineral its blue color. Do you know what mineral that is?
Turquoise? Turquoise?
Maybe this is turquoise. I was thinking maybe this is malachite. I don't know. But whatever it is, color, the origin of the color comes from complexes. In fact, rubies, do you know what gives rubies its red color? A coordination complex. And so these are a lot more common. You know, vitamin C. Vitamin C is a coordination compound. Hemoglobin, coordination compound. A whole bunch of coordination compounds in nature. And so we'll just look at the first three sections. 24.1, 24.2, and 3, which deals with Werner. Werner, he came up with the theory of coordination compounds. He actually won the Nobel Prize for his theory. You know, these were kind of a mysterious set of compounds until he figured out how they were structured. 24.2 deals with ligands. Ligands is a fancy name for Lewis bases. And 24.3 deals with nomenclature of these things. Then we're going to come back to chapter 24 later on in the semester. Move that. All right, so let's see. Werner's theory of coordination compounds. Well, what's a theory? Anyway. One.
After a whole bunch of patterns and experiments is something that hasn't been able to be distributed so far. So it has stood, nothing has been proven that it's not wrong.
Okay. All right. Sometimes things are disproven, but aren't necessarily theories. Like the law of thermodynamics, the first law, second law, third law of thermodynamics. Is that theory? You know, people have been trying to disprove the law of thermodynamics for a very long time, but haven't. And since they have been unsuccessful, I mean, this is what, a couple of hundred years? Since they've been unsuccessful at disproving the law of thermodynamics, does that mean now the first law of thermodynamics, energy is neither created nor destroyed? That's a theory. No, it doesn't. It's still a law. You know, laws are different than theory. And so what's the difference between the theory and a law? It's not that it's been, you know, that it's withstood the test of time. A theory has to do two things. What two things does a theory have to do? Predict. Yeah, good. Cool. What else? You're on a roll. It's good.
And stop there.
Stop there. Well, how do you predict things? How do you predict new things? Well, you got to understand how they work. Once you understand how they work, then you can make some prediction. And so the theory, yeah, it involves testing, but testing is not really, you know, you could test anything, and that's not necessarily theory, right? And so theory has to be a fundamental description of how things work, you know. And then fundamental description of the underlying phenomena. And so he came up with a fundamental description. And in fact, he was looking at the structure. Once you understand the structure of these things, then we can make some predictions. So since we don't quite understand the structure of these things, we don't necessarily make predictions just yet. And so let's take a look at these. Just this COCl3. What do you call COCl3? What's the name of that? Cobalt trichloride, you say? When you use the di, tri, tetra prefixes, you use that for all compounds or just specific compounds? And what type of compounds do you use those for? Covalent. And so is this a covalent compound, COCl3? Or what other types of compounds are there? I just want to review a little bit of Chem 1A. Go along. But what other types of compounds are there other than covalent? There's ionic. And so why do I care whether it's covalent or ionic? You know, it doesn't matter. Covalent or ionic.
Covalent involves gaseous compound?
No. Not just gaseous, but shared, yeah. Covalent, a lot of covalents are gases. Oxygen, whatever else. Those are elements, I mean, like carbon monoxide. But diamond's also covalent. And diamond's definitely a solid. And so, do you know why we care? Why I care? Is this covalent? There's covalent. There's ionic. What else is there? Molecular. Metallic. That's good. What else? What would diamond be called? I guess you could call it covalent, but we have another word for it. Yeah, network covalent. The reason why we care is it network covalent, ionic, molecular is because those are different structures. And different structures will give you different properties. You know, chemists are very concerned about structure, properties, composition, structure, and properties. And so we first need to identify what type of compound this is to figure out the structure. And so what is the structure of this? If I drew this, you know, some people might say, okay, cobalt, this cobalt chloride compound should be, let's say, cobalt trichloride. If you call this cobalt trichloride, this is what the structure I'd be leaning towards because, you know, like carbon dioxide, carbon monoxide, cobalt trichloride. You know, you think you have molecules of COCl3 molecules packed together. And when you think about molecular solids are like ice. You know, ice is water molecules packed together. You think they're soft, you know, it's easy to crush ice. They have low melting points, you know, compared to like diamond. And so if I'm starting to think, okay, cobalt, this is a molecular compound, therefore this should be a molecular solid, I'm already starting to predict, you know, that this should be low melting, should be soft, that kind of stuff. And so would you say that it's a molecular compound? No, because you know molecular compounds, most molecular compounds, and there are exceptions, but most molecular compounds are going to be compounds of non-metals, right? Like carbon monoxide. Carbon's a non-metal, oxygen's a non-metal. Nitrogen dioxide, both non-metals. But cobalt is not a non-metal. Cobalt is a metal. And so when you have a metal and a non-metal, then typically it's a ionic compound. And so all of a sudden, you know, I'm thinking ionic compound, then my picture of this has changed dramatically, because no longer am I thinking soft, low melting, like ice or something like that. Now I'm thinking ionic compounds are like sodium chloride. Is it easy to melt sodium chloride compared to an ice crystal? No, it's much harder. You need much higher temperature. Right? Why? The bonds are a lot stronger. Molecular solids are only held together by intermolecular forces. Ionic solids are held together by ionic bonds. And so is this the correct structure? If I'm thinking that this is an ionic compound, is this the right structure for this? A trigonal planar? Is this actually, is
No.
it?
So it should be like one cobalt and then without a bond. So and it's like a big, like it's like concentric. It's not sexual.
Okay. Let me back up for just a second. I put the octet. Oh, that's right. Cobalt doesn't have an octet. Well, actually, before I get to yours, let's re-examine this, because maybe I drew this wrong. Maybe there should there be a lone pair here, because then it'll complete the octet. Is that good? Well, you know, chapter 24 is described at the end of the book because these, you know, and this is why Werner won the Nobel Prize for these structures, because these structures are a little different than the ones you've already dealt with. And also, some of the things that you've learned we don't use the exact same analysis for these transition metal complexes that you used in earlier chapters. For example, formal charge, octets, oxidation states. These are thought of a little differently. And so the first thing I'm going to ask you is this, you know, how many valence electrons does cobalt have? I know that chlorine has 7 valence electrons. We'll look at the periodic table. Now tell me how many valence electrons cobalt has. Two? 1? I heard 1, 2, what else? Actually, let me, you know what, I need to take a quick survey, because this helps me just figure out how much time I need to spend on talking about valence electrons. 9? Okay. What else? 9? Well, actually, let me just figure out what people are thinking. Just asking. Valerie, how many valence? And if you don't know, that's fine. Just say don't know, or just take a guess. All right, let me show you where cobalt is. I know it's hard to see this table. Cobalt's number 27. I can't pull that off. Right in the middle, almost in the middle of the transition metal block, right here. How many valence electrons?
11?
11?
I mean,
Well, you could just say around 11. That's fine. I mean, it's hard to see, definitely. Maureen?
Oh, wait, there's, okay, this is one,
1?
yeah.
Do you want to change it? Or stick with
I
it?
just started thinking about SP3, all that stuff, and.
Right. I would think, maybe it's SP. What is this?
It's been too long. It's SP2.
Okay. Maybe it's SP2, or maybe it is, you're right, maybe it is SP3. SP3, throw in a lone pair here, that would make this SP3. SP3. But, when we have SP3, we've got to figure out how many electrons to put in those SP3 orbitals, and that's why we need to know how many valence electrons cobalt has. And so I don't know if this structure is right, but if I didn't draw this structure, how many valence electrons for cobalt in this compound? Let's see. Maureen?
Oh, I'm sorry. I guess
One.
it's one. I'm brain hurting.
No, it's fine. The 1's fine. Mackenzie? I just want to get an idea because I'll tell you, I asked the same question in the morning, nobody got it. It's fine, but I want to see what most people are thinking.
You want to follow through and guess?
Yeah, guess. Just take your best guess. There's a multiple choice. 2? 1?
I was thinking sort of 3.
2 or 3? That's fine. Jay? 2? Yusef? 2? Justin?
3.
John Carr?
6.
6? And Jonna? 2? Sang? 2? Kishmer? Isa?
I'll go with 2.
Frankie? Rosa? June?
2 or 3?
Yen? 2? Fook? 3? Ken? 9? Alma?
2?
Olivia? Sylvia?
2?
Mana? Craig? 2 to 3? David?
2.
Claudia?
I'm gonna say 5.
Yanandra?
2.
Hillary?
6.
Kelsey? Hannah?
2.
Hui? Who? Hoy? Hui? 3? Okay, other one? 2? All right, a lot of people wrote 2 down. So how do you get 2 valence electrons? I mean, cobalt's way out here. Does someone want to explain to me how they got 2?
Because it is a transition metal, and like for the transition metal, the electron fill the inside orbit, not the outside orbit. So that's not.
Okay. And what are the inside, what are the outside orbitals for cobalt? Let's first look at the electron configuration, if we're talking the orbitals. And so what was the electron configuration for cobalt again?
4s2.
Okay, so the argon,
And then
4s2, 3d7.
So it should be 2.
And so it fills the inside first and then the outside? Is that right?
No, I think it fills the outside first, and then like after.
It fills the outside first and then the inside?
Yes. Yeah.
Okay, if it filled the outside first, then it'd be argon 3d 9?
No, I mean like you feel the fourth orbit of the two, and then like it begins to feel the third orbit.
Okay,
For the fourth and the third.
Yeah.
like that?
That's what it's-
Okay. And so some people said 9 valence electrons. Right? So the 2 and the 7 is 9.
Yeah.
Are you?
That kind of looks good because argon would be the core, and then these would be the valence. Well, you know, because of this, there are two systems for writing electron configuration. You know, I could have written this electron configuration this way: argon 3d7 4s2. And so, are these the same or different?
The same.
Yeah, these are the same. You're allowed to write either one. They both say the same thing. And so why are there two conventions? Because here we don't fill the 3Ds first, we filled the 4s. But why are the 3Ds written before the 4s? We go left to right. Not lower energy. It has to do with the definition of valence electrons. So somebody remind me, what is the definition of a valence electron? The electron in the highest energy level. That's one way. Another way of thinking about it is it's the outermost electron. And if we think about this, you know, which is further out from the nucleus, the 3D or the 4s? And so if we're thinking in terms of floors, you know, first floor, second floor, third floor, fourth floor, the fourth floor is furthest out. And so these are the outermost. And so the reason it's written this way is to show the difference between core and valence. Valence electrons are going to have the highest energy level, the highest N. Now, if that's the case, then why doesn't the 3D fill before the 4s? Why does the 4s, which are further out, you know, you're filling the 4s, which are further out from the nucleus. And how much farther? Well, we can just use the, do you guys remember the probability, the most probable distance from the nucleus? The probability density function, or the radial distribution function? You guys remember that? Basically, it says this: n equals 1. N equals 2 would be 2 squared out. So the most probable distance would be 4 times. N equals 3, 9 times. N equals 4, 16 times. And so an N equals 3 electron should be about 9 times the distance as an N equals 1 from the nucleus. And then N equals 4 should be about 16 times. We can't pinpoint the electron because of the Heisenberg uncertainty principle, but we're just saying the most probable distance based on the probability density function of the RDF. I know it's been a while probably, so, but this is back in chapter, I forgot what chapter, 11, I think it is. Okay, so these are going to be further, you know, just crude approximation, ballpark, 16 times, this is 9 times, so these are further out. And so these would be the valence. So if an oxidizer comes along, oxidizers like to take electrons, oxidizers are going to take the 4s electrons before they take the 3d electrons. Okay, now I told you that it's farther out. So, but why does something 16 times out fill before something 9 times out? Shouldn't you fill the ones that are closer to the nucleus rather than filling the ones that are farther? Why do the ones farther from the nucleus fill before the ones closer to the nucleus? Someone want to explain that to me, because there's a conflict.
The electrons repel each other in the shell?
Well, all electrons repel each other.
Enough to where they repel each other?
That's not exactly it. Why would the 4s fill before the 3d?
Lower energy level? Or something?
Well, it is lower.
S is more penetrating.
Yes. That's why. Remember all that stuff about
Penetrating and shielding.
right, penetrating and shielding. 4s is more penetrating, even though it's more farther out. And that has to do with the probability density function or the radial distribution function. And so this boils down to this. If it were cobalt, it would have 2 valence electrons. And so cobalt 2 plus is a very common charge for cobalt. Cobalt 3 plus also exists. You know, but cobalt 3 plus would lose these and lose one of the Ds. Cobalt 4 plus isn't very common. All right, so if this were cobalt, but it's not. This should be cobalt 3 plus. This is not neutral cobalt. And so cobalt 3 plus chemically, is it the same as cobalt metal? No, it's totally different. For example, if you needed more sodium in your diet, you know, is it okay to take sodium metal in place of sodium ion? No, because I mean, you put sodium metal in your mouth, it's going to ignite into a flame, basically, right? And so you wouldn't want to eat sodium metal because they're totally different, sodium metal and sodium ion. Well, it's the same thing here. Cobalt 3 is totally different than cobalt metal. In fact, do you know, let me tell you, a lot of these chemical properties you just learn through experience, that is, you just memorize it. And so one of the chemical properties of cobalt 3 is it's an exceptionally powerful oxidizer. Cobalt 3 is too powerful of an oxidizer to exist stably in water. What happens is the cobalt 3 will attack water molecules and oxidize those to form oxygen gas. And so this stuff is totally unstable in water. There's ways to stabilize cobalt 3 in water. You can stabilize it by forming complexes, which is the topic of today's chapter. It's like gold. You know, how can you dissolve gold? You know, gold 3 ions are totally unstable in water. Gold 3 is such a powerful oxidizer, it'll eat up the water. One way you can stabilize gold is by complexing it, and then you can get gold to dissolve. And so we'll talk about those complexes later, but for right now, let's just talk about cobalt 3. What is the electron configuration for cobalt 3? Well, which electrons do we ionize first? So cobalt lost 3 electrons. Do we take 3d electrons? So it would be 4s2, 3d6. So somebody said six valence electrons. That sounds about right. Or do we take 2 of the s's and 1 of the d's? 2 of the s's and 1 of the d's. Good. And so it's going to be argon 3d6. Now, how many valence electrons does cobalt 3 have? And so somebody said 6. In a way, that's correct. In a way, it's wrong, though, too. In a way, it's correct because now the outermost electrons, it only has 6 outermost electrons, right? But in a way, it's wrong because, for example, sodium ion, sodium plus, how many valence electrons does sodium plus have? Some people might say 8 because that's the next outermost level, 8. But it doesn't. Sodium ion should have 0 valence electrons because it had 1, 3s1, it lost it. And now it's down to the argon core. The same thing here. Cobalt 3, it had 2 and lost those plus 1 core. So how many valence electrons does cobalt 3 have? 0. Right? It's just like sodium. Maybe I need to write that up here. Sodium is, what is sodium? Neon? 3s1. Sodium ion is neon. How many valence electrons does sodium ion have? Well, I don't know. I guess you could go helium 2s2 2p6 and say 8. You want to say 8?
It works, yeah.
Well, that's the same thing here. It's a little bit ambiguous. I guess you could say 6, but technically people don't. Technically people say that sodium ion has lost its single valence electron, and therefore it has 0 valence electrons now. And so when we write the Lewis structure for sodium metal, we write 1 dot for sodium metal. When we write the Lewis structure for sodium ion, we write, and so this was mentioned earlier, then we write that, no valence electrons. And so, yeah, this is just, this science is part of this is back and forth stuff, so. And this is a little bit tricky, so I would say cobalt-3 has no valence electrons. In fact, for a lot of these transition modeling complexes, you know, the metals have been ionized, so none of them have valence electrons. Those first two are easy to lose. They're gone. There are some transition metals that have a +1 charge, like silver. But silver has an unusual electron configuration, right? Silver has the 3D. Yeah, good, Claudia, you remember that. And so it only had 1 valence electron to begin with, and it loses it, so we get silver plus. All right, so that's this. And so I wouldn't, where did these 2 extra electrons come from? Nowhere. You know, this is it here. This would be the structure. It would be less than an octet, then we'd be good. But is this the structure for a ionic compound? No. These are covalent bonds. Covalent bonds. We usually show those with a line. And so how do we represent an ionic compound using Lewis structure? Well, the way ionic compounds are represented using Lewis structures is we write the Lewis symbol for cobalt. Now cobalt we'd write, how many valence electrons are we going to put on cobalt? No, cobalt-3 plus, I should say. 0. And so it's just CO brackets 3 plus. Then we have chloride. How many valence electrons does chloride have? 8. So this chloride has 8 valence electrons. We'll write it 8 dots around it, showing it's 8 valence electrons. It has an octet. And so this would be cobalt and chloride. And now I need to bond these with an ionic bond. So how should I show the ionic bond? Do I draw a line connecting them? Is that correct? No. The ionic bond is shown like this. This is the ionic bond. What's holding these 2 together? Don't I need some kind of string or line to hold them together? No. What holds these 2 together? Yeah. The positive and the negative charge attract each other, and that's what's going to hold them together. That's it. Well, it turns out that what happens if another chloride comes along? If another chloride comes along, it will ionically bond to the cobalt. And a third chloride comes along and an ionically bonds. So now I have my cobalt-3 chloride, right? We use the nomenclature rules for ionic compounds. We'll call this cobalt-3 chloride. Okay, now what happens if a 4th chloride comes and bonds? If a 4th chloride comes and bonds, will it be bonded? Will a 4th chloride bond to the cobalt? Is that even possible? Only 3 chlorides should bond, right? And so I got to ask you, what's preventing a 4th chloride from bonding? Overall, this thing has a neutral charge. But if I were to magnify and shrink myself down, is that a neutral cobalt? No. And so what happens is a 4th chloride can come in and ionically bond, and there's no difference. Do you see these? These 4 bonds are exactly the same. All you have is a positive ball being attracted to negative balls. And if you're a positive ball, I mean, why bond in the first place? Why do bonds form? to stabilize it. It's like if you needed to supplement your diet with sodium, could you go to the nutrition store and buy a bottle of sodium ions? I just want the sodium ions. I don't want the chloride because I'm trying to cut down on salt. Is that possible to do? No, because it'd be terribly unstable, right? You'd have such a high static charge, such a high voltage, you'd get quite a shock out of that. And so here, what happens is, well, this is a positive charge here. There's going to be another chloride that sticks up here and another chloride that goes underneath. And so that gives us a total of how many chlorides? I can fit around that. 6. And so it looks like each cobalt is bonded to 6 chlorides. And so do you remember the structure of sodium chloride? If I had a mole of sodium chloride, 1 mole of sodium chloride has 1 mole of sodium chloride ionic bonds. And so let's say I want to break all the bonds in 1 mole of sodium chloride. I'd have to break 1 mole of ionic bonds. True or false? False. How many would I have to break? Do you remember the sodium chloride lattice? The sodium chloride lattice had a sodium ion and 6 chloride ions surrounding it. And so would I have to break 6? Because, you know, here, just imagine this as sodium, break 6. And then imagine this as a sodium. Let's bring another cobalt here. There's nothing preventing this cobalt from coming and being attracted to these chlorides, right? The charge is still there. And so each chloride is actually bonded to 6 cobalts. 4 in the plane here, 1 on top, 1 underneath. Just like in the rock salt lattice, in the sodium chloride lattice, you have, actually, are we out of time? Okay, let me just finish with this. We had 6, coordination number of 6 for the sodium ions, coordination number of 6 for the chloride. So that means we have to break 6 bonds. Is that true or false? So 1 mole of sodium chloride requires me to break 6 ionic bonds. True or false? 6 moles. True or false? False. So then it must be 12. True or false? False. And so what is the number? And the answer is there is no number because we use a different expression for these. The expression we use is in order to break all the bonds in 1 mole of sodium chloride, we have to break a lattice of bonds. And so I'll talk about what a lattice of bonds is next time. And then we're going to continue our Chem 1A analysis of cobalt-3 chloride. So stop there.